Thank you, and I hope you can all hear me well, and thank you for the kind invitation. So given this is an audience a little bit outside my home turf, I've tried to tailor the presentation to go over some basic principles of what you can do in different levels of complexity using micro-extrusion 3D printing, which is the technique that most people refer to as bioprinting. So the title of my talk is Multi-Material 3D Printing of Instrumented and Biohybrid Tissues, and I will get to why the title is. But in terms of topics I will cover, I would like to cover something about cell instructive substrates and materials, how you can print those, which is the kind of lowest complexity. Then we move to what's called embedded 3D printing, which is, I think, the technique that will give you the most versatility in terms of biological complexity. And then I will end on kind of my own kind of special niche, which is trying to use the same tools for integrating electronic sensors and stimulators into microphysiological systems. So the basic principle of micro-extrusion is the same as the principle you apply every morning when you brush your teeth, or evening, I don't know, where you squeeze the material out that liquefies when you squeeze it. So many foams and pastes and materials have this ability that when you don't push them, they don't flow. But when you push them, they liquefy. And this is what we see here in a rheological plot, where you, at a certain yield stress, the material starts to flow. And that's what's happening when you squeeze out a material here. And most 3D printing works on this basic principle. And you can use this to print relatively small structures. If you take a small enough needle that you squeeze out a material, you can, for instance, make small lines. And those lines can be a simple method to develop substrates for instance, generating anisotropic muscle tissues. So we are very interested in my lab in cardiac and skeletal muscle. So this is a very easy and very easy to implement method for building tissue models that replicate the anisotropic structure you find in vivo. But there is a fundamental thing here, is that the smaller features you print, because it's a robot moving back and forth, ultimately the smaller features you try to make, the longer the production times are. So we've been interested in trying to explore how we can tune the material itself to more rapidly or more easily guide the formation of anisotropic muscle tissues. So here's an example of a study we did a couple years back looking at skeletal muscle cultures. So it's relatively well understood that if you want to achieve long-term culture of contractile skeletal muscle fibers, then you typically employ soft deformable substrates. And the conventional wisdom is that you want to match the stiffness to the native stiffness of the muscle. But we found something interesting, which is if you actually go below this stiffness where the soft substrate you apply is deformable to the tissue, then you get very large degree of spontaneous self-organization of the muscle fibers. So this is a 1 millimeter scale where you can see if you culture skeletal muscle derived from myoblasts on a regular dish, you get some degree of alignment, shorter fibers. You get the same for physiological range stiffnesses. But if you go below, you actually see much longer and much more physiologically relevant fibers. And that you can then implement in 3D printing, where we say, now if we print with these soft substrates, can we then direct the patterns to fit into different systems? I'll get to that later. But we would like to have control over the direction of the muscle fibers. And indeed we can, but now we can print lines that are spaced by hundreds of micrometers. That means that it's much faster to implement. So it might take a couple of minutes to transfer your well plate into something that will give you nice muscle tissues. What we found that was interesting is that this self-organization, here's a color code that shows the direction of the muscle fibers. It's not, as one would expect for very tiny structures, parallel to the structures, but actually has an angle to it. So that means if you print circles, then you actually end up with a spiral, which is kind of nice, but we would like to have a little bit more control than that. And so we turn to another kind of fundamental principle, which is when you extrude a material, if you have an anisotropic object in there, that will be aligned to the flow profile that's going on inside the nozzle here. So that means that if you have an anisotropic particle or a fiber, whatever, that will typically align with the shear. And this is an idea that was made famous by Sidney Gladman a couple of years ago in Nature Materials, where she showed these beautiful self-folding flowers that were essentially programmed mechanically due to the alignment of microfibular cellulose. And when you print microfibular cellulose, it looks a little bit like this. So it's not really good for imaging and cell culture. So we were interested in seeing, like, can we apply this principle to organize skeletal muscle tissue, but with getting transparency. And the way we did that was to gradually decrease the size of these fibers here by a slow oxidation process, where we can squeeze the size of the fibers down to the point where we can now print something which is transparent. And then the next question, of course, is can we use that to align cells? And yes, we can. So essentially we print different composites that has these fibers in, and then they become mechanically anisotropic. And that means that now we can print all kinds of tissue patterns. Here's a checkerboard, color-coded for the myotube orientation. And if we print a circle, as I showed before, now it actually is a circle and not a spiral. So that's kind of some basic principles that you can apply for interesting cell culture substrates that can very easily be implemented in regular dishes. But obviously, much of the things that we are promised from the bioprinting community is higher complexity models. So that means the way we actually are printing the cells and trying to build something more 3D, and you can use these anisotropic fibers to make very nice, for instance, muscle fibers. 3-dimensional ones. And that brings me to the next topic of the talk, which is that there are some fundamental trade-offs here in terms of nice printing materials and nice cell viability. So typically, if you want to squeeze a material out of nozzle that has to maintain its shape, we work with high viscosity materials. That translates to high shear forces upon cells upon extrusion. So that means that if you have a perfect print material, usually your cells will either die or be exposed to detrimental mechanical transduction during the printing. So, and this is an inherent problem. So the best workaround that came up a couple of years ago is to use what's called embedded printing, where now instead of relying on your toothpaste to maintain the shape, you actually are printing your cells into a support bath that has these low yield stress rheology that I mentioned in the beginning to maintain the shape. So that means now the cells can be this purple thing, which can have low viscosity. So that means nice for the cells. And then this support bath ensures that you can print precise 3D structures. And when we started our approach to this, we noticed that most of these supports actually didn't have a lot of biological functions. So Janko, who's the first author of this paper, tried to come up with ways where you can turn this bath into an extracellular matrix. And essentially, the solution that he came up with is to combine what's called microgranular hydrogels, so small hydrogel particles that are broken into pieces and then compacted into a semi-solid, and then combine that with ECM components, for instance, collagen. Because the collagen solution has an inherent viscosity, then you can actually have these granular components that tend to be very compact be more dilute. So you can still have high fidelity 3D printing, same as you can in the conventional systems. But now we have a continuous phase, which is dominated by an extracellular protein. So that means cell can now grow in the 3D environment. So we can position the cells and allow the cells to grow and reformulate the environment. And he was particularly interested in neuronal tissue culture. So here's an example where you can show that we can print human stem cell-derived neurons in 3-dimensional patterns, and we can have over time outgrowth of axons in this 3D environment. And that can be used, for instance, to make 3D models of different components or compartments of the brain. And the demonstration for that was to print like two different, an astrocyte type cell and a neuron type cell in different patterns, and look at how they develop and connect over time. And what's interesting is that they maintain this phenotype over culture for months in these 3D supports. And the last part that I think is what we're focusing on a lot right now is we would, of course, like to be able to perfuse these. So not only pattern cells in 3D, but also perfuse them to make sure that we can have growth and long-term culture. And that's also possible. At least we have some indications now that we can actually perfuse these extracellular-like 3D gels that are compatible with embedded 3D printing. Yes. So the last kind of vignette I would like to cover today is how you can also think about adding extra function by putting in functional materials. So that mainly means electrically active materials. And there we often rely on a third principle. So instead of relying on the shear thinning toothpaste like rheology, we actually think more about nail polish. Nail polish is a very good method for making thin uniform films of a material, and making thin films can be a useful way to integrate electronics because they tend to be stiffer than the tissues, and we would like them to then be still deformable. That means we need to shrink their dimensions, but that also ensures a way to kind of control where you are printing, but only in thin films. And this we developed for making some microphysiological systems of mimicking the human heart. And now this movie is not playing. I can try to start it again. Maybe I go back and forth. No. Anyway, so the concept here is that we have a multi-layer 3D printed cantilever that inside has a very soft deformable electronic wire. And then on the surface, we have these anisotropic coatings that guide cardiac cells into an anisotropic tissue resembling that found in vivo. And when these cells contract, the whole cantilever is deflected and the resistance of the wire is increased. And that means we can now build platforms where we have several tissues with a real-time readout of contractility in the form of resistance. And here's the fabrication process as it looks. This is obviously a special 3D printer unique for this, but you can print in this single micron resolution in the thickness dimension by relying on this nail polish principle. And then we can integrate here the wire. Here's some small structures for aligning tissue. And then we can build microwells and connecting electronics around. And we can use that to now monitor real time from the incubator how the tissue develops in terms of contractility, spontaneous beat rate, because these are stem cell derived, but also match that to the other phenotypic markers, such as how the sarcomeres are developing over time. So obviously an increase in contractile force should also be seen as more mature sarcomeres, which is indeed what we see in the tissue. And you can obviously use this also as a drug screening platform. And we ran through a lot, but here's just two examples of known cardiotoxic drugs and their expected response in terms of inotropic and chronotropic responses of the cardiomyocytes. Since then, I worked on several other follow-up inks that have several benefits, but one of the things that we're particularly interested in is to use this nail polish principle to do freestanding structures. So by combining this toothpaste concept and this nail polish solvent evaporation concept, you can actually move these flexible, highly flexible electronics into 3D. So here's a graphite composite, which is very soft and very elastic, but that we can drag in several millimeters in space. And we're using those now to build electronic scaffolds where we can integrate now 3D electronics into, in this case, a bioprinted skeletal muscle for, again, using electronics for recording and stimulating the tissue. So I think that was it. So this is my group, and this is the funding, and I'm happy to take, any questions. I hope I managed to keep within time.